Okay, so open this part. So Wilson Dev Burma, have you got the PDF?
Yes, sir.
Okay, and I hope you have IS 456 with you.
Yes, sir.
Okay, so now you check this problem. So in this problem, this part I think all of you have solved it. This moment of resistance, then up to this part, area of steel. I hope all of you can do it because this part is very simple. I hope all of you can do up to this part. AST, up to AST, area of steel provided. I hope if you go through the problem, you will understand, and I explain this part also. And then also if you have any problem, you can ask me. Okay. So now I will explain this part. Check for deflection. Okay. So now for doing this check, first we have to find out the percentage of steel. Okay. So percentage of steel, what is the formula for percentage of steel? It is 100 AST by B into D. Okay. So 100 in this problem, AST, this is AST provided. Okay. We have to consider AST provided, not the required one. How much area of steel we are providing, that value we have to use. Okay. So 100 AST, that means AST provided, it is 942 divided by B into D. B is 250 and D we have got, in this case, in this problem, it is 462. Okay, so we have got the percentage of steel is 0.8%. Okay, so next we have to find out this Fs. What is this Fs? Okay, so now for finding out this value, we have to go through IS 456. We have to go through IS 456. Okay, so all of you go to clause number, I think 20. Yeah, go to this clause. Clause number 23.2. All of you go to clause number 23.2. Check control of deflection. Okay, so have you got the clause, all of you? Have you got the clause number 23.2? Yes, sir. Benison. Okay, yes, sir. Okay, so now we have to find out, we have to use this graph. This graph we have to use for finding out the stress in steel. Okay, this one we have to find out this Fs. Fs is stress in steel. Okay, so there is a formula given by IS 456. It is 0.58 into Fy into area of cross section of steel required. Okay, AST required divided by AST provided. Okay, so first we will find out this value Fs. So in this problem, our, you can see here, formula is 0.58 Fy AST required divided by AST provided. So if you put all the values, Fy value is 415, AST required is 833. This is the value of AST required. Okay, and AST provided is how much? 942. Okay, 942. So if you use this, if you put the values, we will get Fs equal to 212 Newton per millimeter. Okay. So now you see IS 456. Now you go to the graph. Now you go to the graph. Now you see here, we need the value of this modification factor. Okay, that means it is modification factor in this case, in this book. It is written by K, small k. So modification factor we need for Fs equal to 212. But in this curve, you can see there is no value corresponding to Fs equal to 212. Okay, so now can you tell me how to find out the value? Can you tell me how to find out the value? It is simple mathematics now. We have the range is given 190 for Fs 190, one curve is given. For Fs 240, one curve is given. Okay, we need the value at 212. Fs equal to 212. So can you tell me how to find out? Or you can see the calculation in the PDF. And do you understand how to do it? How do they have done this calculation? You see the calculation and you tell me whether you have understood or not. This is a very simple mathematics involved here. Okay, see the calculation and you ask me if you have any doubt. Hello.
Sir, what is this KZ and KF?
K KT. Hello.
KG, sir, that K suffix something.
Yeah, T for tension. Okay, because you can see here in the graph, we are considering the tension reinforcement. Okay. Therefore, modification factor, it is written for K. And since we are considering tension reinforcement, because it is a singly reinforced beam, so suffix is written T. Okay, T for tension. Okay, so now for Fs equal to 190, Kt equal to 1.35. So do you know how we have got this value 1.35 and 1.2? You see the graph. These values are from graph. For 190, it is 1.35. You can see. Okay, so now 1.35 means we have to see for percentage, because our percentage of steel is 0.8%. Okay, so for this in this line you have to see what are the values. Okay, so for 190, you can see this value. You can see this value corresponding to this value. Wait. 0.8 for this value. How to write here? For 0.8 we need the value here. We need the value. We need this value, and for 240 we need this value. Okay, so now okay, so now you see for this value, for now this is the line for fs equal to 190. Okay, so now for if fs equal to 190, when the percentage of steel is 0.8, what is the value of k? You can see here at this point. Okay, so now for fs this value is approximately, this is 1.2, this is 1.4, this is 1.6, so it will be around 1.3 or 1.35. They have assumed that they have taken it as 1.35. Okay, so if you use the graph, then only you can find out this value exactly. Okay, you have to measure this distance, then you have corresponding to this point, what is the value of k here, you can find it here. Then similarly for fs equal to 240, you can find out the value here. It will be around 1 point something, 1.1 or 1 point something, 1.2, yeah, 1.2 and 1.35. Okay, so now you have got the values for fs equal to 190 and for fs equal to 240. So but we need the value at fs, that means stress in steel, for 212. So how to do it? This, and you know that this value will be less than 1.35. Okay, from this graph your fs value of 212 will be between these two curves. Okay, so that means this value will be less than 1.35. So therefore while doing the calculation, you can see here 1.35 minus, that means this is the deducted portion. Okay, so after, and this procedure is known as interpolation. This procedure is known as interpolation. That means if two values are given, okay, and if you need one value between those two given values, then whatever procedure is followed, that procedure is known as interpolation. So here also we have to do interpolation to find out the value of fs equal to 212. Okay, so after doing the interpolation, we have got that for fs equal to 212, modification factor we have got as 1.29. Okay, so now how to find out the next part? So after getting the modification factor, what we have to do, we have to find out this ratio L by D max. That means maximum value of L by D ratio for this beam. Okay, so now in this, since this is a simply supported beam, so L by D ratio is actually according to IS 456, it is 20. You can see here L by D ratio for a simply supported beam up to a span of 10 meter, it is, you can see here For a simply supported beam up to span of 10 meter, L by D ratio is 20. Okay, so the maximum value will be L by D max will be equal to 20 into modification factor. So modification factor we have got 1.29. It will be 25.8. That means for this beam the maximum value of L by D ratio can be 25.8. Okay. So now we have to check what is the ratio of L by D provided. Okay. So L is given 6000. D, how much D is we are providing? 462. This value 462. So you find out the value, you will get 12.9. Okay, this is the provided value and the maximum value was 25.8. That means L by D max is more than L by D provided. That means our design is correct. Okay. Okay, so now do you have any doubt in this step? Anyone have any doubt in this step? If you have any doubt, you tell me. If you have any doubt in this step, you ask me. Okay, so if you have any doubt, you ask me, okay? If you have any doubt in this part, you can ask me. Actually, this is a very simple step only. Only you need to find out the value of modification factor. The remaining portion is very easy. Hello. Do you have any doubt? You ask me, okay? Do you have any doubt or you can go to the next step? Okay, so next we have to design for shear. After doing the check for deflection, we have to design the shear reinforcement. And this shear reinforcement I will not explain again because I have in the previous chapter we have done so many numericals on this, and I have shared the PDF with you also. Okay, the shear reinforcement I will not explain here. Shear reinforcement I'm not going to explain here because in the last chapter is on shear reinforcement only. So I hope all of you can do it. The remaining design of shear. Okay, but finally what we have to do, we have to write down the design summary. Okay, after designing the beam, after doing all the calculations, we have to write down the design summary. That means what is the beam size, what is the main tensile bars, that means how many bars you are providing in the tension zone. In this case, in this problem, it was 3 numbers of 20 mm diameter bars. Then shear stirrups, that means reinforcement, 8 mm two-legged at 300 mm center to center. and then anchor bars. Okay, so anyone, can you tell me, anyone, can you tell me what is this anchor bars? Anyone? Can you tell me what is anchor bars? Anyone? Don't know, sir. Okay, so you just okay. Okay, now you see this is a singly reinforced beam. Okay, this is a singly reinforced beam, and also that means we are providing main reinforcement at the tension zone, and also we have to provide shear reinforcement. Okay, so if you are providing shear reinforcement, so and if you have reinforcement only on one side, can you provide the shear reinforcement? Can it hold the shear reinforcement or stirrups? Because according to the definition, in our singly reinforced beam, we will provide the main reinforcement below the neutral axis or at the bottom of the beam. Okay, and also we are providing stirrups or shear reinforcement. So can you do that? Can you can the tension bars will hold the shear reinforcement?
No, sir.
No. That means these anchor bars, where we will provide these anchor bars? Can you guess or can you imagine the cross section of a beam? That means we are providing three reinforcement at the bottom, and we are providing shear reinforcement. So these anchor bars, can you assume? Can you imagine where we have to provide these anchor bars? Hmm? Can you imagine the cross section of a beam? We have three reinforcement at the bottom. We have shear reinforcement or stirrups. So now can you imagine we are providing some anchor bars. So in which portion we have to provide those anchor bars? We have to provide at the top. Okay, where otherwise how you can hold those shear reinforcement or stirrups? If you don't have anything at the top portion of the beam and you are providing these stirrups or shear reinforcement, then who will hold that reinforcement? There must be something at the top, na, by which we can bind those shear stirrups or stirrups, because at the bottom we have reinforcement where we can bind the stirrups. But at the top, if you don't have any reinforcement, then how we will bind those reinforcement? How we will bind those stirrups? Okay, so at the top also we have to provide minimum reinforcement to hold those stirrups or shear reinforcement. Okay, those bars are known as anchor bars. Okay, so anchor bars will be of a smaller diameter than the main bars. You can see here the main bars are 20 diameter bars, but anchor bars are 10 diameter bars. Okay, and we have to provide minimum two numbers, because if you provide only one, it cannot hold the stirrups. Okay, so we have to provide minimum two number of anchor bars in a single reinforced beam to hold the shear reinforcement, or the stirrups. Okay, and that anchor bars will be always provided at the top of the beam or at the compression zone. Okay, so do you understand now the anchor bars? Anchor bars are provided at the compression zone to hold the shear stirrups or shear reinforcement. Okay, otherwise if you don't have anything at the top, you cannot bind those stirrups. Okay, okay, so now this is all about your singly reinforced beam. So now I will show you one question from last year final exam. Okay, and I will give you this question as a homework. So all of you will try to solve it. Okay. Two 2016. Yeah, this is the question. Design, this is the question. All of you write this question. Okay, all of you write this question and you try to solve it by yourself. Okay, all of you try to solve it by yourself. This is the question. In the exam, you are asked to find out by working stress method, but I am giving you this to solve it by limit state method. Okay, question number 6. Question number 6, all of you write it down, and I have shared the PDF with you also. You go through the PDF and you design the rectangular beam. Okay, and I will write one thing. You can see here, design a rectangular RC beam. RC means reinforced concrete beam with all the necessary checks, which is simply supported on masonry walls of thickness 300 mm, 300 mm and 5 meter apart. It has to support a live load of this much and dead load of this much, in addition to its self weight. Okay, so use M20 concrete and Fe415 HYSD bars. Okay, so all of you will try to solve this question. Okay, but if you have any doubt in any step, you can always ask me. Okay, so I hope all of you have written down the question. Is it? Okay, I hope all of you have written down the question. Yes or no? Written, sir. Okay. Benison said he has written the question. So all of you try to solve the question. Okay. In this question, you have to design the beam and also you have to check also. You have to check for deflection. You have to check for shear reinforcement and also you have to write down the design summary of the beam. Okay. So you try to solve this question and then if you face any difficulty or any problem in any step, you can always ask me. Okay. Okay, so thank you. This is all about today's class, and from next class we will start to design the doubly reinforced beam by limit state method. Okay, we will solve or we will design the doubly reinforced beam by limit state method. Okay, but by the next class you try to solve this question. Okay, okay then. Thank you everyone for attending the class. Okay, I hope all of you have understood whatever we have discussed today. Okay, thank you.